So we did a recap of Bayesian linear regression before then diving into Gaussian processes. Then we phrased the regression problem, so finding a posterior distribution on the underlying function that we are interested in as an inference problem. That requires us to look at Bayes' theorem. So Bayes' theorem contains priors, likelihoods, posteriors, and marginal likelihoods. And then in the context of Gaussian process regression, we went through all of these components in some detail. And then in the end, we looked at how to make predictions with the Gaussian process, either by sampling from the prior or also sampling from the posterior distribution. Today, we want to look at some of the more intricate details of how things actually work together. So we discussed to some degree yesterday length scales or amplitude parameters, so how they influence the functions that we can model with the Gaussian process. So these are the parameters of the covariance function or the kernel. And there were also questions already yesterday that came up of along the lines of like, how do we actually set the length scale to the right value? And that is exactly what we're going to look at today. So we are looking at something called model selection. So how do we choose a good length scale, or how do we choose a good covariance function? And that all falls under the category of model selection. So we're going to start at maybe choosing good hyperparameters for a given kernel. So it will turn out that in order to find good hyperparameters, we're going to maximize the marginal likelihood. So the marginal likelihood from yesterday will come back to us today. We're going to have a closer look at the marginal likelihood and maybe try to understand why the marginal likelihood is meaningful as an objective to optimize when we want to find good hyperparameters. And then towards the end, we're going to look at how we choose good covariance functions. And then at the end of the lecture, we're going to look at some limitations and maybe some practical guidelines when you work with Gaussian processes, and briefly mention a bunch of application areas. Let's dive in and start with the model selection part. And I want to maybe motivate what we are actually doing here. We are not interested so much, at least, in the training error, but we're interested in generalization properties, so making predictions beyond the training data set. And in our case now with the Gaussian process, but also with the Bayesian in the linear regression setting, we get a predictive distribution. When we make predictions at some points x star, so test input x star, we predict y star, and we can now measure the generalization error by looking at the full predictive distribution. We're going to look more specifically at the log predictive density. So this is the number that's going to be shown in the top right corner, which is the log p of y star given x star and the training data and one specific length scale. So I'm explicitly now mentioning the length scale here as well. Because this is a synthetic example, we can, so this data set that we have, so training data are the dots, and test data may be the green crosses. And what we're going to measure now is the log predictive density of the predicted labels, so the y star labels at the corresponding inputs. So for different length scales and different data sets. Now we're choosing one length scale, and we're going to generate some prior samples from the Gaussian process prior. And so you've seen these kind of functions before. So these are typical functions that we would expect to get from our Gaussian process prior. So now we're going to make predictions from the posterior distribution, which you compute based on the training data here. And then we evaluate the quality of our prediction on the test data. And we're going to get this LPD value, the log predictive density of, in this case, of 0.14. And what we want to have is we want to have a log predictive density that is relatively high. So higher is better here. I'm going to now do the same thing here. So I'm going to keep the same data set, training and test data set, but I'm going to change the length scale now. So what you can see, or what we can see now, is if we make the length scale shorter, right? So our functions look a bit more wiggly in some sense, and the posterior Gaussian process would be indicated here on the right-hand side. And what we can see is that with the shorter length scale, we have the model becomes a bit more flexible. So also you can see this in the prior samples. With long length scales, we have slowly varying functions, and with shorter length scales, we then also have faster varying functions, and that gives us a bit more flexibility in terms of like what we can model. But so that's kind of like what's mentioned here. With a shorter length scale, we have a more flexible model. But what you can also see, if we compare this to the previous slide, the error bars increase much faster. So here the error bars, for example, are much higher. So the training data are these orange disks. If we go away from the training data with a longer length scale, the error bars they don't change really that much. But if we make the length scale shorter, the error bars go up quite significantly. So with a more flexible model, we also get faster increase in uncertainty away from the data. And then generally, this doesn't mean we have good generalization properties, but more like bad generalization properties in the sense that we cannot really transfer much knowledge from the data that we observed to other data points. So from the training data to the test data. Shorter length scale means that I only need to move very little in input space for function values to become uncorrelated. And that means that the information transfer that I can do from the training data to the test data is relatively low. And that's kind of like what the last point means here. And so the log predictive density also measures this, or gives a numerical value to this. With the previous length scale, we had 0.14 as a log predictive density. Now we have 0.06, so that is lower. So this fit is actually worse than the one before. And we can go a bit more extreme and make the length scale even shorter. So you can see how super flexible these models are. And then our log predictive density is minus 0.43, so that's even worse. And now you can also see that there's pretty much no generalization, or not much generalization going on. So the error bars between the data point, even between the training data points where there are no significant gaps, they explode. And there's not much knowledge transfer going on far away from the training data. For this particular data set, we would then say maybe the first fit is the best one. So this looks like a meaningful fit. It's a relatively simple model that explains the data. Error bars make some sense. The mean also makes sense. This one is visibly worse, and this one looks pretty horrible. One would almost say this is overfitting. So if we now change the data set, so we're going to look at a different data set, and we're going to use this example with the 3 length scales that we used here. Now our training data set are these orange disks again, and our test set are these green, again, these green crosses. Now, if we look at the longer length scale again, then our log predictive density is minus 1.19. And we can see that, for example, these areas down here, they are not really well covered, neither in the training set nor in the test set. So this model is actually pretty bad at predicting these values down here. And so that maybe is an indicator that the model class is not rich enough. So we may want to look at a more flexible model and want to decrease our length scale. So if we do this, so this is a shorter length scale, so the same medium-sized length scale that we had before. And now we can see that the training data is reasonably well modeled, and the predictions also make some sense. Most of the green crosses are within these shaded error bars. So that's a relatively good model given the training set, or given the data set that we have, and the log predictive density also indicates this. We came from minus 1.1 to minus 0.03. So this is a much better value compared to the other one. But now we can look at an even shorter length scale, and then we get something like a fit that looks like this. Again, so the test data, the training data and the test data are definitely under, or make sense under the GP distribution. but the GP is a bit too flexible even for modeling this data. And the log predictive density indicates this again. So we would not actually choose this particular model if we just looked at the log predictive density. And now we can look at maybe a third data set where now our training data are again these orange disks. And we start again with the long length scale. And we can, I think it's very clear from here that this model is pretty horrible in fitting the training set or the test set. And so the log predictive density is far in the negative. So minus 16.6 is actually a pretty bad value. If we decrease the length scale, so make the model class a bit richer, then it looks a bit better, but we are still missing out on data points in various regions, and not even the training data is modeled super well. But the log predictive density is significantly better, so we're now at minus 3.35. And we can then say maybe we want to increase the flexibility of the model further by decreasing the length scale. So if we do that, then we get a model that looks like this. It's not really great, but the data set is modeled significantly better. And the log predictive density also indicates that, let's say, if we had to choose between these 3 different length scales, then we would choose this short length scale for modeling this kind of data set, or for describing this kind of data set. The summary of this kind of like exercise or visualization is that we can make predictions that are equipped with uncertainty. We also looked at like how the choice of the prior, for example, the length scales, influences the predictions we can make. And we saw that for different regression problems, so we looked at 3 different regression problems, we may require different kind of priors, so different setting of the length scale in this particular example. The question that we want to look at is really, how do we select a good prior? And when we talk about priors, we're going to talk about 2 different things today. We can talk about choosing hyperparameters of the Gaussian process, which are the parameters of the kernel and maybe the parameters of the mean function. I'm going to focus only on the parameters of the kernel and maybe the likelihood. So length scale and amplitude parameter of the kernel, or periodicity parameter of the kernel, and the noise variance in the likelihood. And then maybe at a different level is like the question, what is actually a good kernel, or what is a good mean function? So the Gaussian process has a bunch of hyperparameters, which we can think of maybe as the parameters of the mean function, but also the parameters of the covariance function, so length scale parameters and signal variances, but also the noise variance in the likelihood. So these are we call them hyperparameters because they control the kind of like the distribution of the function, but they do not directly control the data. So they are higher level parameters. In the Gaussian process setting, we can think of the function itself to be the set of parameters if we compare this with the Bayesian linear regression setting. And so these hyperparameters are higher level parameters in that sense. When we talk about training a Gaussian process, which you may see somewhere will also come up later, it's basically about finding a good set of hyperparameters. And then we can talk about higher level model selection for mean and covariance functions. And so the automated statistician already kind of automates this in some way. Let me maybe draw a picture of what we have up to this point. So we have some observed data. So the Y values are observed values. And so I just mark this as a gray node to indicate that this is an observed value. Right, so these are observed function values, noisy. So then we have the function itself. So that function is an unobserved quantity. So I'm just going to make this a non-gray node. So that's the unobserved an observed function. Something we call that also a latent function. In the Gaussian process case, we have these kind of hyperparameters, so the length scale parameters. So the length scale parameters control the distribution of the function. So we can maybe draw it in this way, that I'm going to use maybe notation like theta as the hyperparameters of the Gaussian process. So these ones are the hyperparameters of the Gaussian process. In the maybe in the corresponding model for linear regression, right? So we also had observed y values, which are the functions. The noisy function values, and then we had a diagram that looked like this, which were these ones were now. So this one is the GP setting, and this one is the linear regression setting. These are the parameters now of the model. And so what did we do to find good parameters of the model? So we did maximum likelihood and map estimation, and in the Bayesian linear regression setting, we were putting a prior distribution on these parameters, and then we were integrating them out. But effectively, we were trying to, if we look at only maximum likelihood and map estimation, we maximized P of y given theta. I'm ignoring all the input values, the x values here. They are currently, they're just disturbing in terms of notation. So that one would be maximizing the likelihood, or we would look at maximizing P of y given theta times P of theta, which would be maximizing the posterior distribution. Now, how are we doing the same or similar things with the Gaussian process? Any suggestions? Is there a way of like maybe using the same ideas that we used here to find good parameters, to find good hyperparameters in the Gaussian process? An idea is like, why don't we try to write down exactly the same equations here on the left-hand side? So why don't we try to find the argmax of P of y given theta? So now theta are the hyperparameters in the GP setting. If we had a direct connection, let's say, which looked like this, without this kind of like stuff in the middle, then we would do maximum likelihood estimation. But we don't have that direct connection from the hyperparameters to the data. Now we have to write down how we get to this particular equation. Any suggestions? Y and f are connected directly, and so theta and f are also connected directly. So we're just going to maybe try to rewrite this particular equation in a slightly different form. So we can maybe write the same thing as P of y comma f given theta, and we integrate out df. So here we have a joint distribution between y and f, and we integrate out f, and then we end up with exactly P of y given theta. Yeah, so similar to P of a is the integral of P of a comma b db. So that's kind of like the marginalization property or marginalization rule that we just used. So we can now use the structure of this graphical model. And we know that in the directed graphical model, each directed arrow is a conditional distribution. So we can now write this as the integral of P of y given f, which would be this arrow here, times P of f given theta, which is this arrow, df. This is again P of y given theta. We exploit the relationship between theta and f and y to write down P of y given theta in this way. So now the question is, does this look familiar?
So it currently looks like the marginal likelihood that we can derive from a Bayes theorem.
Mm-hmm. That's right. So this is the marginal likelihood. So that is exactly right. And we came to the marginal likelihood now through a completely different way, where we effectively wanted to do maximum likelihood estimation on the hyperparameters given the data. So it turns out that the marginal likelihood is the objective function if we wanted to do some sort of like some form of maximum likelihood estimation on the hyperparameters. So it's not exactly maximum likelihood because the likelihood would only be this term here. But in order to get the theta parameters in, we also need to look at the prior distribution. So this is the GP prior. And previously, we never conditioned on the theta parameters, but they were implicitly always there because we always use a kernel or a covariance function and a mean function. But they would have been very misleading in the equations that we had before. But the GP prior is always conditioned on the, for example, the length scale parameters. Now, the other question that we had was, what happens if we actually now look at map estimation in the linear regression setting? How does that now translate into kind of like map estimation in some form in the Gaussian process setting? What do we require in map estimation?
So in the case of linear regression, we require the prior on the parameter.
Exactly. So we require a prior distribution on theta. Prior on theta plus Bayes theorem will then allow us to derive the map estimator. That's exactly the approach that we would also take in the Gaussian process when we can place a prior distribution on the hyperparameters, for example, the length scale parameters, and then use Bayes theorem to compute the posterior distribution. This kind of slide summarizes what we wrote down a few minutes ago. So we have the y values over here, these observed values. We have the f value here. And then I'm just splitting up the hyperparameters that we are looking at for the time being. So we have psi parameters, which are the length scale and the amplitude, for example. And I explicitly put in the noise variance as well as an additional hyperparameter. And we're just going to summarize both of these things in the theta parameter. As you said before, we are now placing a prior distribution on the set of hyperparameters here. And then we can find the posterior distribution, which is this blue distribution. So P of theta given x and y. We use Bayes theorem here. It's P of theta times P of y given x and theta divided by P of y given x. The orange block here is exactly the marginal likelihood that we computed yesterday. So it's P of y given f and f of x basically times P of f given theta. So that orange block is the same marginal likelihood that we looked at yesterday. I'm just going to copy this posterior distribution over from the previous slide. So the marginal likelihood in this orange block here is the integral of the likelihood evaluated at the training set times the prior distribution evaluated at the training set. And now I'm explicitly conditioning the prior distribution on the theta parameters, on the length scale and amplitude parameters. If we want to maximize the posterior distribution on the hyperparameters, then it is sufficient to, or it's equivalent to maximizing the log posterior distribution with respect to the hyperparameters, and that would require us to maximize the numerator of this expression. So the log prior plus the log marginal likelihood. So that is this expression down here. And if we now choose a uniform prior, on the theta parameters, then P of theta would be constant everywhere. Then maximizing the posterior distribution would be equivalent to maximizing the marginal likelihood. And that is something similar that we also had in linear regression, where we said that the maximum likelihood estimator and the map estimator are identical if we had a uniform prior distribution on the parameters. So this is also called maximum likelihood type 2 because there is this close correspondence between maximum likelihood and marginal likelihood optimization, but just at a different level. So the spirit is the same thing. The equation that we optimize is the same thing, but there's a very important difference by optimizing the marginal likelihood, and the properties of the marginal likelihood will be super critical later on when we come to regularization and stuff like this, because unlike the maximum likelihood estimator, which tends to overfitting because it only looks at the training error, the marginal likelihood has an automatic regularization term in there. The marginal likelihood in the Gaussian process is actually easy to compute. It turns out to be just a number, and I'm just going to write this down as an kind of like functional relationship here. So this is actually not a probability distribution, but just a real number because the y values are observed. We can now learn the Gaussian process hyperparameters by maximizing the log marginal likelihood. And so the log marginal likelihood is given by this expression here. There is the -1/2 y transpose k inverse times y. So just defining this k theta as k plus sigma n squared times I, -1/2 log determinant of k theta plus constant. And I'm having the subscript theta on the k because that's the only place where the hyperparameters show up, which are in these k theta terms. The next question is like, how do we maximize or optimize the marginal likelihood? How do we solve optimization problems? Suggestions?
You differentiate with respect to the parameter and set it equals to 0.
Yep, that is exactly what is happening here. What we normally do is we compute the partial derivatives of the log marginal likelihood with respect to the individual hyperparameters and set it to 0. The derivative is given here. I mean, the derivation is going to take a little bit, but I just wanted to write down the equations for you so you don't have to worry too much about it. When you say set it to 0, do you think you can solve for theta directly and say theta equals, something that is similar to a maximum likelihood estimator where we wrote down, was it theta is x transpose x inverse times x transpose y? Do you think we can do the same thing here where we write down optimal theta parameters are the following? Finding a closed form solution is not possible here, but we can use gradient descent to find at least local optima of the marginal likelihood. So there's no closed form solution, but we can use gradient descent for finding the good values. So all parameters that parameterize your kernel function or mean function, they would show up here. Given that we have now looked at the maths and the derivation of how to optimize hyperparameters, let's see what happens here. We are going to look at this kind of example where our training data is given by these blue crosses, and we have initialized our Gaussian process to some length scale, some noise, and some signal variance, so the amplitude parameter. And now we're going to run gradient descent on the log marginal likelihood. We're going to look at the first term over here, so y transpose k inverse times y, which is going to be we're going to call this the data fit term, and I'm going to explain on the next slide why that is the case. And the number which is behind elbow is the log marginal likelihood. What we would expect is that the log marginal likelihood gets better as we now run gradient descent on our hyperparameters. And then you can also see what the posterior Gaussian process looks like. So at the moment with this particular initialization of the hyperparameters, the posterior mean is the orange line, and the posterior uncertainty is indicated by these shaded arrow bars or shaded regions. Let's run gradient descent on this. You can see that the log marginal likelihood gets better, so it gets higher. And so this fit looks pretty good already. But you can also see now the data fit term gets worse. We want to have higher data fit, but overall the marginal likelihood term increases. So initially with our very short length scale, we can model the data extremely well. So the data fit term is very high. But the marginal likelihood value is really bad in the beginning. So we need to make a compromise between fitting the data and getting good marginal likelihood values. And we want to now have a look why that is the case. So the fit in the end also looks much more meaningful than before. So this one in the beginning, if you look at this, it looks a little bit like overfitting, right? So at least the posterior mean nicely hits the data. The posterior mean is overfitting. But the marginal likelihood values are not ideal. And if we run gradient descent, we would get a fit that looks significantly different and much better, actually, also in terms of like generalization properties. And so now the question is, why is this? And we're going to look at the marginal likelihood at, we're just going to and see what kind of properties the marginal likelihood actually has. We're copying from previous slide the marginal likelihood term, and I'm highlighting two particular terms over here. The first one, this is a quadratic term, is we call earlier as a data fit term, and this term measures whether an observation y with training observation y is within the variation allowed by the prior distribution. Effectively, that measures whether we can model the data. The second term is the determinant. The determinant is the product of the variances of the prior, and therefore it also computes the volume of the prior. If you now think of maybe a volume as the richness of the model class, then we can take this term as a penalty on the model complexity. And that kind of like ties back to the question that we had early on. What do we mean by like model complexity? How do we measure this? So this term in the marginal likelihood is exactly this penalty term on the model complexity class, this log determinant term. So if we want to maximize now the log marginal likelihood, so maximizing the first term means to bring this term to as close to 0 as possible. So because the y transpose k inverse times y, that term is non-negative, we have a minus in front of this, so this will always be smaller than 0 or smaller equal than 0. Getting this as close to 0 as possible is the idea. And then the other term here is the log determinant term, which we subtract from this term. So the log determinant term ideally goes to something that is negative. We want to make the volume of k as small as possible. Well, that means we restrict the model class to something that is relatively simple. What that means is that the marginal likelihood kind of like automatically trades off between fitting the data, which is this quadratic term, and taking care of the model complexity, which is this log determinant term. If we think back to ridge regression or map estimation, we had this the penalty on the parameters, on the amplitude of the parameters, so the norm of the parameters. That would correspond to the model complexity term. The data fit term is the same that came from the likelihood, and the penalty on the amplitude of the prior can be interpreted as the complexity of the model. So the more flexibility we give the parameters, the range of the parameters, the more flexible the model. And in the similar way, we can interpret this log determinant term. I also want to have a brief look at the marginal likelihood surface. So this is the marginal likelihood surface on 2 dimensions, where we have the noise value on the horizontal axis, the length scale on the vertical axis, for a given data set. And what we see here, I mean, it's a bit difficult to see, but maybe on the web, it's a bit easier to see. We have 3 local optima here. And so that means, in the first place, the marginal likelihood may give us different answers depending on where we start our optimization. But I was now wondering whether you could give me some idea what kind of models you would expect in these cases. What would the Gaussian process look like if we were to choose this particular noise value and this particular length scale? And I can tell you that the data lies between +5 and -5. If we choose a length scale that is, let's say, maybe 10 and a relatively high noise value, what would that mean for the Gaussian process? For every combination of noise and length scale, we have an optimal amplitude, but let's just ignore the amplitude for the time being.
Because the length scale is high, so I will expect something that will not vary too much.
Yeah, okay, so that's an excellent start. So we have very long length scales. So we have a function or a GP that doesn't really change much. We have something that, varies maybe very slowly. Is that kind of like, that's what you said, right? So now we have a lot of uncertainty, which means that basically, if these are the uncertainty bars, I mean, if the data was looking like this, then we completely ignore the signal in the data and just treat everything as noise. So that's kind of like what things look like. Now let's have a look at a different example, maybe the one down here. So assuming our data looks like this, what would the corresponding function look like? So we have relatively little noise, we have a relatively short length scale. What do you think the corresponding GP would look like? So we have more complexity or more flexibility because the length scale is short, right? So what would you expect the GP to look like here? So, okay, so this here at the bottom is an explanation of the of this particular configuration of noise and length scale. If we, ignoring all the variances, but this is kind of like what the posterior mean could look like. And so what happens here at the bottom right? What happens here? What would a function look like if we again were to draw some function values here? What could the function look like? So in the top right, we have long length scale, high noise, bottom left, short length scale and very little noise. And now here we are in kind of like a regime where we still have actually quite a lot of noise, but the length scale is a bit shorter. So what could it look like?
I was expecting smoothness, but still having a larger. So the error bars will still be a little bit large, something like that.
Okay, so that also looks good, and we still have a lot of noise in here as well. The explanations of what we had is actually, so they are very good. So we had the one example here in the top is a very long length scale, and everything or much of this is modeled with noise. And if you look at the log marginal likelihood value, it's -1.28. Here at the bottom right, we have still a lot of noise, but the length scale is a bit shorter, so you can see that the function varies a little bit faster. The marginal likelihood value is a little bit better than up here. And here at the bottom left, we have very low noise and a lot of and a very short length scale. The function can vary relatively quickly, and so the fit is really good. So the marginal likelihood value here is -1.22. So according to this data set, the bottom left fit would be the best, but you can see that the marginal likelihood values are actually relatively similar. So we would find 3 different explanations of the data that kind of makes sense. And here's a 4th example where we just have a value here in this yellow area, which I said earlier, this is pretty bad. And it's really bad because the data is not really explained by the Gaussian process. So even if the length scale is maybe okay, the uncertainty is not high enough to explain the data. And so the marginal likelihood also expresses this by a really high negative value and say this is a really bad place to be. So, and maybe if you want to go, if you want to go to this website, you can play around with this kind of diagram a little bit more. And so here we have this kind of the surface plot of the marginal likelihood, and we modified the colors a little bit so it's a bit easier to see. And you can click within this range, and you can see the corresponding fit here on the left-hand side. And you can really play around with what the corresponding fits would look like if you were to be, let's say, totally extreme. For example, you choose a very short length scale and with very high a very low noise. So then this would be pretty bad. Long length scale with high noise. So all of this you can play around with. So to maybe summarize bits and pieces that we have seen here is that the marginal likelihood is non-convex, right? So we have like theoretically multiple optima, local optima. And especially in the small data regime, the GP can end up in about 3 different situations when we optimize the hyperparameters. And maybe some of these 3 are kind of like reflected in the marginal likelihood plot that we saw earlier. So either we end up with short length scales and low noise. So we have a highly nonlinear mean function with little noise around it. Long length scale with high noise, where we effectively treat the signal to be just noise. So there's no real signal in the data, but most of what we see is considered to be noise. And some sort of like hybrid where we have maybe shorter length scales and a bit of noise, which kind of like interpolates between these 2 extremes. And because of this, it's worthwhile restarting the hyperparameter optimization from random initializations to kind of like find the best expression or the best value of the marginal likelihood. If you increase the data set size, then maybe 2 of these local optima disappear, and you end up with 1 explanation of the data. So the more data you have, the more peaked the posterior distribution over the hyperparameters is, or the more unique the optimum of the marginal likelihood surface. We could maybe think about integrating out the hyperparameters as well, because instead of like what we did in Bayesian linear regression, at some point said, okay, let's just not optimize the hyperparameters. We placed a prior on them, and then we integrated them out. So that was Bayesian linear regression. The problem here is that we can't do this anymore. We have no closed form solution. And we could do this approximately, for example, by using Markov chain Monte Carlo sampling, but that is relatively expensive. And maybe worthwhile doing this in the low data regime where we have multiple different optima. We kind of like want to take everything into account. But if in the high data regime, it's probably not worthwhile because the hyperparameter posterior is relatively peaked, and then we can just use a point estimate. So that's fine. In a low data regime, it would make sense to integrate them out, but it's a bit complicated and computationally heavy. So I also wanted to recap a bit more on like why the marginal likelihood seems to be working. Starting from like early on today, we were talking about generalization performance on unseen test data. So we looked at the log predictive density, and we at test data to motivate using some sort of like model selection. But the marginal likelihood doesn't actually know anything about test data, but it seems to be working relatively fine. Just looking at the training error is not a good idea. So because we end up in overfitting situations if we do a maximum likelihood. If we just add uncertainty to our predictions, it also doesn't really help if the model is wrong. So maybe an example looks maybe like this, right? So we add uncertainty to our predictions. The model is wrong in the sense that the hyperparameters don't make much sense. We don't get good generalization performance. We just add a lot of uncertainty to our predictions. The kind of like knowledge transfer from, or information transfer from the training data to test data is very low here. But if we make a prediction, let's say maybe at minus 3.5, or even minus 3, we would just say, I have no idea what's going on. So adding uncertainty by itself doesn't really help if the model is completely wrong. But what it does is it makes our predictions more cautious by saying, well, I don't actually know what's happening. So that is what adding uncertainty does. And the marginal likelihood seems to find a relatively good balance between fitting the data and finding a simple model. And therefore, it kind of like implements as a practical implementation of Occam's razor. But what does Occam's razor say? If you have multiple explanations of your data, choose the one that is the simplest. And that is exactly the trade-off between fitting the data and finding a simple model. And now what I want to look at now is I want to find out why the marginal likelihood leads to models that generalize well. So we already saw there is this kind of like trade-off between data fit and model complexity in the marginal likelihood term. But I maybe also want to give another look at, or perspective on, the marginal likelihood as a predictive model. More specifically, I want to look at the equation of the marginal likelihood. This is the marginal likelihood. I'm ignoring the x values here. What this equation says is it's the probability density function of the training targets given the parameters, or hyperparameters in this case. This is the marginal likelihood. And so this vector y is just a collection of n different training observations. What we can do now is we can factorize this. I can write a joint distribution P of A comma B as P of A given B times P of B. So we're going to do the same thing here. We're going to write this as P of Y1 times P of Y2 given Y1. So this is P of Y1 comma Y2, so that's a joint distribution here, times P of Y3 given Y1 comma Y2. So now this one would be now the joint distribution of PY1 comma Y2 comma Y3. And then we can continue like this. So just keep multiplying things together up to P of Yn given Y1 up to Yn minus 1.
But where's the parameter?
Oh yeah, sorry, I keep forgetting the parameters. Yes. Yeah, so that's correct. So sorry about that. That's kind of like what I wrote down here as well. So same thing that we just did, and we can summarize this or write this in a more slightly more compact form, where we just start with P of Y1 given theta, and then we have a product of P of Yn given all previous n's also conditioned on theta. By looking at this expression, we can think of this as a sequence model, right? So where data arrives sequentially, where we start with P of Y1, and then once Y1 has arrived, maybe Y2 comes next, and so on and so forth. If we think of this as a sequence model, then we can think of the marginal likelihood to be composed of sequential predictions. And it predicts the, let's say, the nth training observation given all previous observations. So Y1 to Yn minus 1, and keeps multiplying things together. And if you then think of this as predicting the training data yn that has not been accounted for, so it is not in our training set yet. We make a prediction, then we effectively treat the next data point as some sort of like test data point, an unobserved quantity. And then we observe it, and then we can condition on it as well. So the intuition now behind this is that if the marginal likelihood continuously predicts well on all n previous points or training data set, it will probably also do a good prediction the next time that happens. We can think of this therefore as a proxy for the generalization error on some unseen test data. And so I want to show you like an example of like how this works. So again, we have this factorization down here of the marginal likelihood. What I'm going to show you here now is a GP conditioned on the training data that we have already observed with fixed length scale, fixed hyperparameters. Now we're going to see observations which are indicated by these red crosses. And the predictive uncertainty is, or 2 times the standard deviation, is indicated by this orange bar. So what we're going to see here now is the log predictive distribution or density, so that's the values that we had earlier, at y1 when we evaluate this orange bar at this red cross is minus 1.7. And what we're going to see here in the second row is the predictive distribution of the current observation given all previous observations. So this empty set will disappear in a moment and will be replaced by observations that we already have in our training set. So if we do this now sequentially, we're going to get something that looks like this, right? So you can see the GP changing. So this upper value is the quality of the individual prediction. And if we sum all of these values up that we have observed, then we get to the value here at the bottom, which is the log marginal likelihood value. If the values are within, I think within a good range of the orange bar, then the predictive quality is good. If the red cross is outside the bar, you will see that this the value gets some sort of like a hit. If you compare these values up here, then some of these values, so there was a -5 something, that was a value that was pretty bad because the red cross was outside or far outside even the orange bar. And so there's also a value -12. If you look at this, that you will identify this because the red cross is far outside the orange bar. Should come soon. There we go. Yeah, so that value was a very bad predictive value, or had a predictive log likelihood. So that's kind of like what the marginal likelihood does. And we can do the same thing again with shorter length scales, longer length scale. Now we can look at the marginal likelihood again as a way of like doing things, and we do exactly the same thing here. We now go from the left to the right and do a predictive distribution of our training data, or the next training data point conditioned on all previous training data points. And now we see how the log marginal likelihood evolves over time, and the log predictive density of this test point, this training point, given the previous test points, is shown here. We just keep summing them up. And we can see that there's pretty much no generalization happening because the length scale is very short, but the marginal likelihood does effectively this sequential prediction here, and sums these predictions up. So if we were now to increase the length scale and make it a very long length scale, then this is what happens. So now we have a slowly varying function with a very long length scale. And we can see also now the marginal likelihood has problems predicting what the next real training point is given the previous data points. And so we we get a lot of penalties for not being able to model the data. Right, so we can optimize the marginal likelihood and then find the optimal length scale. And if we do that, then the marginal likelihood predictions would look like this, these sequential predictions. And we can see that the training data is relatively well predicted. Yeah, there's still some noise available here, but yeah. So this kind of like fit looks much more sensible than any of the other fits that we had earlier. So that's how the marginal likelihood can be interpreted as a sequential prediction model on the training data set. If we look at these kind of like 3 examples that we had here with short length scale, long length scale, and optimal length scale, and see what the marginal likelihood values look like as a function of the number of data points that we add. So in the beginning, the marginal likelihood values kind of like agree with in all of these 3 settings. And then we can see that the long length scale marginal likelihood value really plummets. So that's a really bad sign. And the short length scale will be significantly different from the optimal length scale. The problem with the short length scale is that it consistently overestimates the variance. Yeah. So if we go back to this example here, right? So it's effectively just adding a lot of noise everywhere, and it needs to do this, but there is no generalization going on. And because there's a lot of noise, there's no high density, right? So when we talk about high density, we normally think that the predictive distribution is relatively concentrated. But here we just have a lot of uncertainty everywhere. So the long length scale consistently underestimates the variances, and most of the observations are outside the error bars, and that's a big problem as well, because then we cannot explain the data. And if we choose the optimal length scale, then that one trades off both behaviors reasonably well, and that is maybe we can also now tie this back to the explanation that we had earlier of like fitting the data and having relatively low model complexity. So in the last part, I would like to start maybe looking at different kinds of model selection. So at the moment, or up to now, we only spoke about hyperparameters, optimizing hyperparameters, but we also need to think about how to choose a good mean function or a good kernels or a covariance function. So now the question is like, how do we find the best kernel, the best mean function? And we have multiple options here at hand. So one of them is to do cross-validations. We can think about using Bayesian information criterion or archaic information criteria, which other people use for non-probabilistic models. But we can also use the marginal likelihood again as a way to compare the quality of kernels and mean functions. And the reasoning comes exactly from the same place that we used earlier from hyperparameters. We can think of the marginal likelihood as a way to sequentially predict the data set. And instead of like changing only the hyperparameters, we can also change the kernel or the mean function. And so that's exactly what we're gonna do now. So we're going to go look at a very simple example. So we are looking at a data set with 8 data points. So these 8 data points here. We're choosing a mean function, so prior mean function to be identical to 0, so that doesn't bother us too much. We use the map hyperparameters for each kernel, or think of this as the maximum marginal likelihood hyperparameters for each kernel. So we train the hyperparameters in the way that we normally do, that we also discussed earlier. And then we're going to look at the log marginal likelihood values for each optimized model. And so optimized model in this case means we're looking at 4 different kernels. So if we use a constant kernel, so that is a kernel that allows us to just add a bias to the function that we want to model. So then we would get a posterior Gaussian process, which looks like this. And that is the optimal bias that we can find, and we would get a log marginal likelihood value of -1.1. So now we can use a linear kernel, so which makes the assumption that the data can be modeled with a straight line. And here we would get a slightly better log marginal likelihood value, which is -1. We could use a Matern kernel, which allows us to model things in a more flexible way. So we use a kernel where we make the assumption that the underlying function is 2 or 3 times differentiable. And then we would get a fit that looks like this. And that looks much more meaningful than just having a linear kernel or a constant kernel where we pretty much say everything is noise. So here we actually have some structure in the model. So here we have a value of -0.86. And if we use the Gaussian kernel or the squared exponential kernel, we get a log marginal likelihood value of about -0.7. So if we just compare the log marginal likelihood values, then we would choose this particular kernel as the correct kernel. So we have training data, which is given by these blue crosses here. And the data is generated from a function which is a linear combination of a smooth function and a periodic function. And it's unclear to us, or we don't know what this kind of like what either the smooth function is, or what the periodic function is, or what these linear parameters are, the theta s and theta p. So, but we can now use a Gaussian process with a kernel which is a sum of 2 kernels. One is the Gaussian kernel and one is the periodic kernel, and then we can add these kind of like theta s and theta p parameters to the kernels. So effectively, if you remember the equations of the individual kernels, then the theta s and theta p parameters would be absorbed in the amplitude parameters, so that they are already weight parameters. By optimizing the marginal likelihood, these theta s and theta p parameters would be automatically optimized as well. Now, if we run our example again from before, you can see that the marginal likelihood value goes up. The fit of the function becomes, or say the distribution over functions becomes more reasonable. And this is kind of like what we find at some point. So this is the posterior distribution, or close to the posterior distribution of the GP. And so what happens here is that the amount of periodicity versus the smoothness is automatically chosen by selecting these hyperparameters theta s and theta p. So they are part of the optimization problem. And what we also see from here is that the marginal likelihood learns how to generalize and not just to fit the data. So data fitting is not the prime objective of the marginal likelihood, but the marginal likelihood also has the model complexity term in it. And at some point it will favor simpler models for more accurately fitting the training data. Yeah, so the fit is relatively good now. The model is relatively simple, but sometimes you can also see that the data fit term actually goes a little bit lower. So now it's going a bit lower, now it's going a bit higher, but the marginal likelihood value always goes up. Towards the end, I would like to look at some limitations and maybe some practical guidelines that may be useful if you work, or when you work with Gaussian processes. So one of the big problems that we have in Gaussian processes is computational and memory complexity. So more specifically, if we have a training set size of n, then training scales cubically in the size of the training data set. Does anyone have an idea why that is the case? When we, just to go back to maybe the training of the GP, right? So we optimize the log marginal likelihood, and that means we need to optimize this expression here. What are the expensive things in this expression? What is expensive to compute here? the thing that we have here, right? So this matrix here is an n by n matrix. And so where n is the size of the training data set. And that means inverse scales in n cube. So computing an inverse is actually a very expensive operation. So that's one of the problems that we have here. Even assuming that we have trained our model, computing predictive distributions is also not super cheap. So it still scales quadratically in the number of data points. And we also need to store the kernel matrix, which is n squared, or the inverse kernel matrix. So it's an n times n matrix, so n squared ballpark values we need to store. And we also need to store the data set, because we always need to compute cross correlations between f of x and f of x star. So storing that requires us n times d, where d is the dimensionality of the input data set. So in practice, you would not be able to run a Gaussian process in this form with more than 10,000 data points. And generally, we're talking about input dimensions of maybe 10, 20. So that's kind of like what you can do without paying any attention to any further details. But there's some work on that kind of like tries to address these issues to scale Gaussian processes to larger data sets. So there's some work on sparse Gaussian processes using something called inducing variables. So I don't want to go into details here, but these kind of methods in combination with mini batching and other things will scale Gaussian processes to millions or even billions of data points. So that is one way to get around or to address this issue of this n equals 10,000 limit. Parallelizing computation is an option. There is some work by James Hensman or Yarin Gal, where they parallelize computations. There are actually also, there's work by Andrew Wilson, which I haven't mentioned here. So they use modern compute hardware, so GPU clusters and incomplete Cholesky decompositions to scale full Gaussian processes. So exactly like this kind of thing here, to also relatively large data sets, I think like 1 million data points. By using incomplete Cholesky decompositions, they would make approximations to the inverse kernel matrix that somebody mentioned earlier, which is the expensive part. There's also some work on running local Gaussian process expert models on subsets of data. So think about this maybe as if you have a very big data set and you just subdivide this into smaller data sets. Let's say each data set has maybe 1,000 data points. Then you could train a Gaussian process model on each of these individual data sets and then try to combine those predictions in the end. So that would also scale to pretty much arbitrarily large data sets. And there's also some work on variational Fourier features by James Hensman and colleagues, which also would address this issue, at least to some degree, in low dimensions for that goes beyond 10,000 data points, training data points. So here are some tips and tricks that you can use. And again, I think we summarized this on the website here as well. You can use domain knowledge to set initial hyperparameters. That means if you have an idea of what your length scale parameter could be, you can initialize the hyperparameter to some meaningful value. You could think about standardizing the input data and then set the initial length scales to about 0.5. You could think about standardizing the targets and then set the initial signal variance to about 1. It is often useful in practice to set the initial noise level to relatively high values because the optimization surface becomes much smoother. So that allows you to simplify the optimization problem of the marginal likelihood to some degree. Random restarts is already something we mentioned earlier. So sometimes we may be running into numerical instabilities. And if you actually look at the justification that we give here on the website, one way to address this issue is to have an extra penalty term on the signal to noise ratio, which is the the amplitude parameter over the standard deviation of the noise value. So if you penalize this, then you have some sort of like regularizer in there, which would otherwise cause the Cholesky decomposition of the K plus sigma n squared I matrix to fail. I also want to maybe towards the end come back to some application areas that maybe where Gaussian processes are kind of useful. So Gaussian processes are used in reinforcement learning and in robotics, for example, to model value functions or transition models with Gaussian processes. Bayesian optimization is another, I think, very prominent example of an area where Gaussian processes are used. Here, the idea is to find high-level parameters of some bigger machine learning models, for example, learning rates in a deep neural network. And here the idea is to model the unknown utility function with GPs. Gaussian processes are an African invention. They came from South Africa, from Wits University. They were invented by a person called Krier. So in the geostatistics literature, it's also called kriging. This person wrote a master's thesis on Gaussian processes for geostatistics. And in the machine learning community, Gaussian processes only showed up in the 90s. But because of the Gaussian process also gives it these kind of like nice error bars or uncertainty estimates. They're also useful for sensor networks. In the context of sensor networks, there's a lot of work on optimal sensor placements, for example, by Andreas Krause. But Gaussian processes are also used for time series modeling and for long-term forecasting, for example, in the context of climate science for weather and climate simulations. Towards the end of the lecture, I wanted to give you maybe one motivating example of like where Gaussian processes are used in reinforcement learning and robotics. So I wanted to show you a little video of some work that we've done a few years ago, where we used Gaussian processes for robotics or for learning optimal control for a robotic system in a reinforcement learning setting. So this thing is called a cart pole system. So you have a cart which is running on this track here, and we have a pendulum attached to the cart, which is freely swinging. And now the idea is to learn a strategy that pushes the cart left and right, that then swings the pendulum up and balances it in this inverted position in the middle of the track. We were collecting data from this system, so state observations, so that's the position velocity of the cart and the position and the velocity of the pendulum, and the control signals that push the cart left and right. And we were learning a transition model that predicts the next state distribution. And then we use this kind of transition model to evaluate the quality of a control strategy at the moment by computing long-term expected rewards. And then we use gradient descent to optimize policy parameters. But what we did in the early stages, we're just like applying random actions to the system. You can see how this thing moves. And then we took these kind of data points that we collected. So we had 50 data points at this point. We now trained this Gaussian process model for learning the transition dynamics. But as you have seen maybe earlier in some of the examples, 50 data points in a 4 or 5 dimensional space is not really that much. And that means we relatively quickly leave the range of the data. That means our predictive uncertainty will explode when we predict long term. But anyway, so we now use this model to predict the expected long-term reward and then optimize the policy, go back to the cart pole system and say, okay, here's a policy, try this one out. So this is what happens the first time. If you look at the variance, it's super useful to understand what happens. So what happened here was that after about maybe 2 or 3 time steps predicting into the future, the variances explode because we enter regions of the state space that we have not seen before. So the model is very uncertain, and then the variances explode and you don't have a meaningful learning signal anymore. But when you apply the controller, you now start collecting data in regions of the state space that you have not seen before. And that means the model that we now update with the new data is much more confident about what happened before. And so now it sees that what happened before was actually a pretty bad idea, and now it tries something else. So again, we use this updated Gaussian process model to compute a long-term reward, and then it finds something else, right? So now it has the idea of like, or got the idea of swinging the pendulum up, but it also now has, for the first time, it actually had data in this regime where things are interesting, right? In a state space where the pendulum was kind of upright, but it was far too fast. But the reward also says, you were far too fast, do something about it. And now we can see over the next couple of trials that it takes this information into account. So every time it runs one of these trials, it updates the Gaussian process model. The Gaussian process model becomes more confident. And with a more confident model, we also get a better control strategy. And then after a few trials, you can really see like an improvement in every trial compared to the previous trial. And with about 15 seconds, it kind of like gets the idea of like swinging the pendulum up and balancing it. And we can run this for a little bit longer and see that it actually solved the problem. And the Gaussian processes we use are the ones we discussed in this lecture. So we use a mean function, which is linear, and a squared exponential kernel that we discussed in a lot of detail in this lecture as well. So there's nothing fancy actually going on.
Every approach has its own advantage, and as in terms of the domain where you can apply it compared to others. So, and I believe the Gaussian process also, we have where we can actually use it and where it won't be a feasible solution, feasible approach for us to take. Can you just elaborate more on that?
Yes, so the Gaussian process is super useful if you have relatively small data sets. You already know that, when we go beyond 10,000, then things become a bit tricky. The second one is the dimensionality of your input features. We haven't really solved the problem of like working on images yet. I would say input dimensionality in an RL problem is limited to, say in practice, maybe 10 to 20. We have successfully solved like higher dimensional problems, like maybe around 30 dimensions. But that's, these are the ballpark numbers you will need to work with if you do this. And the third constraint is that we need to choose kernels that allow us to model the underlying function relatively well. In many cases that may be fine, but there are some cases, some functions where the Gaussian process will have difficulties modeling the right thing. If your function looks like this, and then you have a jump. So this kind of function is very difficult to model. I think for anything, even a neural network will have problems with this. If we try to model functions like this in an RL setting with a Gaussian process, we will have problems. And then I think the RL wouldn't work that well. So if we have smooth functions in relatively low dimensions, then I think the Gaussian process is a very good choice for doing model learning in reinforcement learning. And otherwise, we may have to think a bit more carefully about what to do. Gaussian processes are, I would say, the gold standard for regression problems. And the reason for this is that they give us reasonable error bars. They are closely related to linear regression, but they automatically trade off data fit and model complexity through the marginal likelihood. And that is actually a really nice thing that the Gaussian process does. While the theory is potentially a little bit difficult to understand, when we actually do our computations, the only thing that we need to do is we need to be able to work with multivariate Gaussian distributions. So there are two things that we need to be able to do, and one, or maybe three things. One is being able to multiply Gaussians together, to condition Gaussians or multivariate Gaussians or joint distributions. And the third thing is to be able to marginalize. So these are the three things that we need. And if we know how to do this, and we can do everything that we discussed today with Gaussian processes. And I also really wanted to make a point about the marginal likelihood as a useful objective that trades off data fit and model complexity. So that's kind of like the end of today's lecture. I have a bunch of references in here, so if you're interested in looking at some of these things, I'm also happy to provide more literature if somebody of you is interested in Gaussian process stuff.